Hello and welcome. I'm Professor JW, and I'm here to tell you about quantum mechanics. If you do like my lecture, please don't forget to subscribe and hit that like button for me. Now, let's get on with the lecture. Quantum mechanics. Quantum mechanics allows the calculation of properties and behavior of physical systems. It is typically applied to microscopic systems, molecules, atoms, and subatomic particles. It has been demonstrated to hold for complex molecules with thousands of atoms, but its application to human beings raises physiological problems such as Wigner's Wagner's friends, and its application to the universe as a whole remains speculative. Predictions of quantum mechanics have been verified experimentally to an extremely high degree of accuracy. For example, the refinement of quantum mechanics for the interaction of light and matter, known as quantum electrodynamics, has been shown to agree with experiment to within 1 part of 1012 when predicting the magnetic properties of an electron. A fundamental feature of the theory is that it usually cannot predict with certainty what will happen, but only give probabilities. Mathematically, a probability is found by taking the square of the absolute value of a complex number known as a probability amplitude. This is known as the Born rule, named after Max Born. For example, a quantum particle like an electron can be described by a wave function which associates to each point in space and probability amplitude. Applying the Born rule to these amplitudes gives a probability density function for the position that the electron will be found to have when the experiment is performed to measure it. This is the best the theory can do. It cannot say for certain where the electron will be found. The Schroeder equation relates the collection of probability amplitudes that pertain to one moment of time to the collection of probability amplitudes that pertain to another. One consequence of the mathematical rules of quantum mechanics is a trade-off in predictability between measurable quantities. The most famous form of this uncertainty principle says that no matter how a quantum particle is prepared or how carefully experiments upon it are arranged, it is impossible it is impossible to have a precise prediction for a measurement of its position and also at the same time for a measurement of its momentum. Another consequence of the mathematical rules of quantum mechanics is the phenomenon of quantum interference, which is often illustrated with the double slit experiment. In the basic version of this experiment, a coherent light source, such as a laser beam, eliminates a plate pierced by two parallel slits, and the light passes through the slits is observed on a screen behind the plate. The wave nature of light causes the light waves passing through the two slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. However, the light is always found to be absorbed at the screen as discrete points, as individual particles rather than waves. The interference patterns appear via the varying density of these particles hit on the screen. Furthermore, versions of the experiment that include detectors at the slits find that each detective photon passes through one slit, as would a classic particle, and not through both slits, as would a wave. However, such experiments demonstrate that particles do not form the interference pattern if one detects which slit they pass through. This behavior is known as wave-particle duality. In addition to light, electrons, atoms, and molecules are all found to exhibit the same dual behavior when fired toward a double slit. Another non-classical phenomenon predicted by quantum mechanics is quantum tunneling. A particle that goes up against a potential barrier can cross it, even if its kinetic energy is smaller than the maximum of the potential. In classic mechanics, this particle would be trapped. Quantum tunneling has several important consequences, enabling radioactive decay, nuclear fusion in stars, in applications such as scanning, tunneling, microscopy, tunnel diode, and tunnel field effect transistor. Get it all out in a minute. How y'all doing tonight? Y'all enjoyed my little lecture? I hope so. I'll tell you, didn't even comb my hair for you. All right, you want some more? When quantum systems interact, the results can be the creation of quantum entanglement. Their properties become so entwined that the description of the whole solely in terms of the individual parts is no longer possible. Erwin Schroeder called entanglement the characteristic trait of quantum mechanics, the one that enforces the entire departure from classic lines of thought. Quantum entanglement enables quantum computing and is part of quantum communication protocols such as quantum key distribution and superdense coding. Contrary to popular misconception, entanglement does not allow sending signals faster than light, as demonstrated by the non-communication theorem. Another possibility opened by entanglement is testing for hidden variables, hypothetical properties more fundamental than the quantities addressed in quantum theory itself, knowledge of which would allow more exact predictions than quantum theory provides. The collection of results most significantly, I can't talk tonight. Going on with that. Most significantly, Bell's theorem have demonstrated that broad classes of such hidden variable theories are in fact incompatible with quantum physics. Need to hear more? Okay. Is it not possible to present these concepts in more than a superficial way without introducing the mathematics involved? Understanding quantum mechanics require not only manipulating complex numbers, but also linear algebra, differential equations, group theory, and other more advanced subjects. Accordingly, this article I'm talking about will present a mathematical formulation of quantum mechanics and survey its application to some useful and oft-studied examples. And I'm going to wrap it up for tonight on this one. I hope you ladies enjoyed it. Have a nice night.